Okay, so let's get started. In this session, we'll look at limits that involve the exponential and logarithm functions that we discussed the last time. Um, One thing that you should know about the behavior of the log and the exponential functions is how they compare to polynomials. And just to recall a few things, the derivative of the log of x is 1 over x, uh, and the derivative of the log of the absolute value of x is also 1 over x. The logarithm function is strictly increasing, and it grows without bound. And so the limit as x goes to infinity of the logarithm of x does not exist, right? The logarithm function just continues to grow without bound. And one way that you can see this, uh, perhaps, is that the function is always strictly increasing. Okay. What happens, so that was the limit. As x goes to infinity, the logarithm function just is unbounded, goes to infinity. What happens as x goes to 0? Well, then the derivative is 1 over x. So the tangent line becomes closer and closer to being vertical. Okay, so there's a vertical asymptote at 0. And then the limit as x goes to 0 from the right, for numbers bigger than 0 and tending towards 0, the logarithm, that limit does not exist. Okay, or you could say that it's going to minus infinity. Okay, continuity of, I recall that the logarithm function is continuous for any argument bigger than 0. So that means that if you were asked what's the limit as x goes to x naught of log of x, it's just log of x naught. It's the function value, okay, because it's continuous. Now, exponential functions, remember we said last time that the derivative of the exponential function is the exponential function. It's the only function that has this property. And the exponential of x is always bigger than 0. So if the derivative is the exponential function, which is bigger than 0, that means that the exponential function is also a strictly increasing function. And it will grow without bound. So the limit as x goes to infinity of exponential of x grows without bound. Okay. In the other direction, as you're going to minus infinity, well, the limit as x goes to minus infinity of the exponential of x equals the limit as x goes to infinity of the exponential of minus x. Now, what's exponential of minus x? It's 1 over the exponential of x. So this is the limit as x goes to infinity of 1 over the exponential of x. So you've got 1 on the top, which is not changing, and on the bottom, you've got something which is just getting larger and larger. So without bound. So the limit as x goes to infinity of the limit is going to be equal to 0.
Understand?
Can you say that again?
Oh, sorry, my mic was unmuted by accident.
All right. And recall again, the exponential function is continuous everywhere, right? Because it's differentiable everywhere, so it's automatically continuous everywhere. So if you're asked what's the limit as x goes to x naught of exponential of x, it's just the function value at x naught. It's continuous everywhere. Okay, so let's suppose that we want to compare how fast these functions are growing. So let's take the limit as x goes to infinity of the logarithm of x over x. Okay, so if I want to compare the logarithm function to the polynomial x, okay, now the numerator is going to infinity and the denominator is going to infinity. So we can use L'Hopital's rule for that, right? Okay. So I write infinity over infinity in square brackets, not because infinities are some sort of a number, but just says has the form infinity over infinity, which means I'm allowed to use L'Hopital's rule to evaluate it. So if I use L'Hopital's rule, this is the limit as x goes to infinity. Derivative of the logarithm of x is 1 over x. The derivative of x is 1. So then this is the limit as x goes to infinity of 1 over x. Well, that's 0. Okay? So the limit as x goes to infinity of logarithm of x over x is 0. So that means that x, one way of phrasing that is to say that x grows much faster than logarithm of x. Yeah, there's a question?
Sir, wasn't log of x reaching infinity undefined?
Yeah, so the logarithm of x, yeah, so I'm not using infinity like a number. The logarithm of x is going to infinity, and x is also going to infinity, okay? So that's why I can use L'Hopital's rule. Both the numerator is going to infinity and the denominator is going to infinity. That means you can use L'Hopital's rule. So you can take the limit, instead of the quotient of the functions, you can take the limit as x goes to infinity of the quotients of the
And sir,
derivative.
we can use L'Hopital's rule for infinity or 0 over 0, right?
That's right. And here we have the form infinity over infinity.
Okay. Okay.
Okay. All right. So if we use L'Hopital's rule,
Sir?
yes.
How's the log of infinity is equal to infinity?
It's not equal to infinity. I'm saying this as the L'Hopital's rule can be used when you have the form 0 over 0. When substitution would either give you 0 over 0 or substitution would give you infinity over infinity. When I write infinity over infinity in square brackets, that's the shorthand for saying the numerator function is growing unbounded, the denominator function is growing unbounded, and I recognize then that this is a situation in which I'm allowed to use L'Hopital's rule. That's what this,
Basically, I'm asking that how log of infinity is equal to infinity, how numerator is equal to infinity. For denominator, it implies that x approaches to infinity. That's fine. But how numerator log of infinity is equal to infinity? That's what
because
I'm asking.
it's growing without bound. It just keeps growing, right?
Okay.
And it keeps growing, and there's no, in the limit, its derivative is always positive, so it's strictly increasing.
Okay. Okay.
Sir,
Yeah. Is there
sir,
another
the
question?
log function is increasing only for positive values, right?
The log function is increasing for all values for which it's defined. If you look at the
Okay.
graph, if you look from left to right, anywhere on the graph, the values of the logarithm are increasing.
Okay, sir.
Yeah? Okay. All right. Now, what about the other way? What if I take the limit as x goes to infinity of x over the logarithm of x? What would happen? Well, that's the reciprocal of what I was doing over there. So if logarithm of x over x was going to 0, what do you think is happening to x over logarithm of x?
It's going to infinity.
This is going to infinity. Yeah. Okay. All right. So any and in fact, any polynomial will grow much faster than the logarithm function. So it's growing, but a logarithm is growing, but it's growing really slowly. Okay. How about this? Powers of x. The limit as x goes to infinity, logarithm of x over x to the n. The numerator function is just growing without bound. The denominator function is growing without bound. So what can I do?
Just pick 0, I guess.
Yeah, it's going to go to 0, right? So logarithm of x over x to the n is the limit as x goes to infinity of this thing that we already know, log of x over x times 1 over x to the n minus 1. We split up the limits, okay? So here's a limit that we know is going to 0. We just found that. And here's also a limit that we know goes to 0. So this is 0 times 0 is equal to 0.
Sir, can you please explain the first step again?
The first step, I broke it up into pieces so that I could get pieces that, so I could get this log of x over x, which I've already just done, right?
Sir, could we apply L'Hopital rule here?
Yeah, you apply you apply L'Hopital's rule, and it will also give you.
Sir, but how did we get log x over x? There was no x over here in the denominator. It was
There's
x raised
log of
power n.
x. There's log of
Yes.
x over x to the n. So that's
Yes.
x times x to the n minus 1.
Oh, yeah. Got
Okay.
it. Hmm.
All right. All right. So once again, logarithm grows much slower than any polynomial function. Okay, what about this one? What do you think? Limit as x goes to infinity of x to the n over the logarithm of x. What do you think that should be?
0.
Infinity.
Yeah,
Infinity.
right. Because x to the n is equal to x times x to the n minus 1. So I've got the x over log of x, which I already had, which I knew goes to infinity, times x to the n minus 1, which is also going to infinity. Okay, so this thing is just blowing up. Okay, what about powers of logarithm compared to x? Okay, limit as x goes to infinity, log of x squared over x. What do you think that is? Before we calculate it. What
0.
Yeah.
Zero seems.
Yeah, even powers of logarithm go slower than the monomial x. Okay, so let's do this. Limit as x goes to infinity, log of x all squared over x. Well, the numerator function is growing without bound. The denominator function is growing without bound. The shorthand for that is to write infinity over infinity in square brackets. Okay, and that means I recognize that I can use L'Hopital's rule to do this. Okay.
Then I have a question. Like,
Yeah.
let's say instead of writing 2 outside the square bracket,
Yeah.
how about we write x instead of 2? Then what would be the answer?
The logarithm of, you mean the logarithm of x to the power x?
Yes, sir, exactly.
Okay, yeah, we'll deal with that in a bit. Okay.
Oh, okay, okay.
Okay. All right. So I use L'Hopital's rule. So the derivative of log of x all squared, well, the derivative of something squared is twice the something times the inner derivative of, so the derivative of log, which is 1 over x, and the derivative of x is 1.
So sorry to interrupt. I guess that would be just 0 as well.
Well, we'll see in a bit. Okay.
Okay, okay, okay.
All right. So that gives you limit as x goes to infinity of twice log of x over x. We've seen log of x over x before, right? So that's going to be 0. Okay. What about if I take the third power of log of x over x, and then I take the limit as x goes to infinity? Well, I'll have to apply L'Hopital twice, maybe, right? Right. So however many powers of L'Hopital you need, how many iterations of L'Hopital you need, you just keep doing L'Hopital over and over again, you'll get the same result. This is going to go to 0. So positive powers of logarithm also grow much slower than the monomial x. Okay, you should try this as an exercise. Okay, and you should see that this goes to 0 also. Okay, now let's take a look at what happens with the exponential function. Okay, what do you think? Limit as x goes to infinity of x over the exponential of x. Okay, how would you tackle this?
Isn't this
0,
also an
I guess.
application of L'Hopital?
Yeah, this should be, I can do this with L'Hopital's, right. So limit as x goes to infinity, x over the exponential of x. Well, x is going to infinity, or x is growing without bound. The numerator function is growing without bound. The denominator function is growing without bound. And the shorthand for saying that is writing infinity over infinity in square brackets. That means I can use my L'Hopital's rule. So this is the limit as x goes to infinity of the derivative of x, which is 1, and the derivative of the exponential function, which is the exponential function. And okay, so 1 just stays at 1, and the exponential grows without bound. So this is going to 0. Okay. Any questions? All right. Okay. What about some positive integer n, x to the n? Limit as x goes to infinity of x to the n over the exponential of x.
0,
Well,
I guess.
yeah, it's going to be 0. I'm just going to keep doing L'Hopital over and over again until I get a constant in the numerator function. And every time I take the derivative of the exponential, I just get the exponential back. Right?
Sir, if you do, so you basically take the derivative n times until you get
Yeah.
x raised
Yeah.
to no power.
That's right. Just apply L'Hopital n times and it'll work. Okay. It'll go to 0.
So, sir, I have a question about that.
Yeah.
Wouldn't that just mean that you have to differentiate n factorial times?
No, I think n times will work.
No, wait, no, that's not n factorial. My bad. My bad.
Right? Okay, so another way of saying this is that if we compare the two functions, the exponential function grows much faster than any polynomial function. Okay, what if I have limit as x goes to infinity of the exponential of x over x? Well,
Is it infinity?
yeah, the reciprocal function was going to 0, so this function will be going to infinity. Will grow with the function grows without bound. So this limit wouldn't exist. Okay, now sometimes you have functions which don't look like, well, there are functions where the L'Hopital can help you, but you might have to take the logarithm of the function first. Okay. So do you remember when we did, last time we did logarithmic differentiation, right? So you had maybe a function of x and then its exponent wasn't just like an integer or something or a real number. The exponent was also a function of x. And taking its derivative, the first thing you did was you took the logarithm of the function and you differentiated that, and then you solved for the derivative of the function that you wanted. And the reason that helped was that taking the logarithm allowed you to pull the exponent downstairs. And then you had a function of x times a function of x to deal with, rather than a function of x to the power of a function of x. Okay? So with some limits, taking the logarithm first can help you. Okay? So here's the problem. Limit as x goes to 0 of 1 plus x to the 1 over x. Okay? So this is not a form that L'Hopital can help you with. All right? But what we can do something else. We can say that I'm going to have the function I'm dealing with is, I'll call it y of x. So y of x is equal to 1 plus x to the 1 over x. The logarithm of this function is the logarithm of 1 plus x to the 1 over x. And then by the rules for exponents, I can pull the 1 over x outside the logarithm. So that's equal to log of 1 plus x over x. So I wouldn't know how to take the limit of y as x goes to 0. But maybe I can take the limit of this function as x goes to 0. Okay? So the limit as x goes to 0 of this function y, log of 1 plus x over x. Now, what if I try a substitution? Then I would, on the top, I would have log of 1. Log of 1 is 0. And on the bottom, I'd have x is equal to 0. So I have this form 0 over 0 if I try substitution. That is a form for which I can use the L'Hopital's rule. Okay? So what's the derivative of log of 1 plus x? It's 1 over 1 plus x. What's the derivative of x? It's 1. Now, limit as x goes to 0 of 1 over 1 plus x is 1. And the limit of 1 is 1. So 1 over 1 equals 1. So I don't know, the limit as x goes to 0 of the logarithm of y is equal to 1. Okay, this is what I've established here. Okay, so the limit, what's the limit of y? The limit as x goes to 0 of y of x equals the limit as x goes to 0 of the exponential of the logarithm of y. Exponential function is continuous everywhere. Logarithm function is continuous everywhere it's defined. So I can pull the limit inside. So it's the exponential of the limit as x goes to 0 of the logarithm of y of x. Well, that's the limit that I just found. That's 1. So this is the exponential of 1, which is the constant that we call e. Okay? So, going back, the limit as x goes to 0 of 1 plus x to the 1 over x is equal to e. Is that okay? Okay. The reason I took the
Sir, can you
logarithm,
go down to the last page, please? The one where you showed the solution.
yeah.
Sir, can you explain this again?
Okay. The exponential and the logarithm cancel each other out, right? They're inverses of each other, right? So y of x is the same as exponential of the logarithm of y, provided that y doesn't take like values like 0 or a negative number. And that's not happening over here. Okay? So the limit as x goes to 0 of y of x equals the limit as x goes to 0 of the exponential of the logarithm of y. Now, why would I want to take the logarithm of y? The reason is that this thing had a function of x to a power of a function of x. And I'm not sure how to handle that, how to take the limit there. But by taking the logarithm, I get a more tractable function. Okay, so.
Sir, can
Yeah.
you go to the next slide?
Yeah, so I pulled down, when I took the logarithm, that allowed me to pull the 1 over x outside the logarithm. So the logarithm of y is a nicer function. It's log of 1 plus x over x. And that allows me, I don't know how to find the limit of y as x goes to 0, but maybe I can find the limit of the logarithm of y. Okay. Well, the limit of the logarithm of y gave me the form 0 over 0, so I could apply L'Hopital's rule, right? And then when I applied L'Hopital's, that's the limit as x goes to 0, 1 over 1 plus x over 1, which is equal to 1. Okay? So the limit as x goes to 0 of y of x is the limit as x goes to 0 of the exponential of the logarithm of y. Now, because exponential is a continuous function, I can pull the limit inside. And what's now inside the exponential, the argument of the exponential, is this limit that I already found, which was equal to 1. So this is equal to the exponential of 1, which is equal to e. Okay? So the logarithm of y goes to 1, so y is tending to e. Okay? There any more
So, sir,
questions?
yes, sir, so basically the answer of this whole equation is e, exponential.
Yes.
Yes.
Okay, let's try another one. The limit as x goes to infinity of 1 plus 1 over x to the x. Right? Now what happens? As x goes to infinity, 1 over x is going to 0. Right? And then if I tried substitution, then this would look like 1 to the infinity. Well, I don't know what to do with 1 to the infinity. Okay? On the other hand, again, you've got a function of x and it's raised to a power of a function of x. So the way to, those may be hard to handle, but one way that you might be able to handle it is if you can pull that function downstairs. Then you've got a function of x times a function of x. And maybe those limits would be easier for you to find. Okay? So I will let y be this function, 1 plus 1 over x to the x, and I will consider the limit of the logarithm of y. Okay? So y of x equals 1 plus 1 over x to the x. I want the limit of y as x goes to infinity. The logarithm of y, when I take the logarithm, I can pull the x outside of the logarithm. That's x times the logarithm of 1 plus 1 over x. Now I don't have any exponent which is giving me any trouble, right? Now I would like to apply L'Hopital's rule to it, right? L'Hopital's work for quotients, right? It works for a function divided by a function. So if I want to rewrite this as a quotient of two functions, I can write it as logarithm of 1 plus 1 over x divided by 1 over x. Okay? So the logarithm of the function I care about is equal to the logarithm of 1 plus 1 over x divided by 1 over x. So is that algebra okay?
Yes. How did you bring the x downstairs?
Well, x is the same as 1 over x, right?
Oh, okay.
Okay. So now let's take now can I find the limit of this as x goes to infinity? Okay, well, the limit as x goes to infinity of the logarithm of y. If I were to plug in infinity as if it was a number, 1 divided by infinity is 0, and 0, and then I would get the logarithm of 1, but logarithm of 1 is 0. And 1 divided by infinity, crudely speaking, is also equal to 0. So I have this form 0 over 0. That means I can apply L'Hopital's to it. Okay? So instead of taking the limit of a quotient of functions, I take the limit of the quotient of the derivatives of the functions. Okay, derivative of the logarithm of 1 plus 1 over x. Well, derivative with respect to u of logarithm of u is 1 over u. Now I have to multiply by the inner derivative. Okay, derivative of 1 plus 1 over x is minus 1 over x squared. And on the bottom, derivative of 1 over x is minus 1 over x squared. Okay, so let's, if I cancel out the minus 1 over x squared, I'm left with the limit as x goes to infinity of 1 plus 1 over x. 1 over x gets vanishingly small as x grows, and that gives me 1 over 1, which is 1. So the limit of the logarithm of y, yeah, Basit has a question?
Yes, sir. Sir, first of all, I have a question that how did we get when we do x approaches to infinity, that 1 over x becomes 0, right?
Yes.
Then that becomes 1 over 1 divided by 1, right? Then minus 1 over x square, isn't that also becomes 0?
Yeah, minus 1 over x squared would also go to 0.
So when 1 multiplied by 0, wouldn't that be 0?
No. No, but it's being also divided by minus 1 over x squared. So you can't just go multiplying by 0 unless you let the bottom one be 0. And then you've got 0 over 0, right? So you can't do that.
So we first have to simplify it until it becomes.
Yeah, you have to simplify it until you can solve it, yeah.
And sir, and the second question is that if we move back to the original expression that
Yeah.
was just the original expression 1 over 1 over x, and when we just even if just put the limit x approaches infinity, well then 1 over x becomes 0, and 1 with the 1 with the power of anything is equal to 1. So
Yeah,
why do we
one to the
substitute
power of any real number is equal to 1. Sure.
so 1 to power of infinity?
Infinity is not an element of the real number system.
Oh, okay, sir.
No such
That
number
was
as
my confusion.
Yeah.
Thank you, sir.
Okay. So yeah. So okay. Any other questions about this one so far? Okay. So if the logarithm of y is tending to 1, then what is y going to?
0, I guess.
0.
E.
It's going
E,
to
sir.
E to raise power is equal to 1, I guess. No, never mind.
Okay. Yeah. So the limit as x goes to infinity of y of x is the limit as x goes to infinity of the exponential of the logarithm of y. Okay, because exponential and logarithm are inverse functions, right? Exponential is a continuous function, so you can pull in the logarithm, or you can pull the limit inside. Now, what you have inside the exponential, the argument of the exponential is a limit that we just found is 1. So this is exponential of 1, which is equal to, which is the number that we call e. Okay. All right. Yeah. Same thing we did before.
Sir,
Yes.
sir, can you go back to the slide number 39?
Yeah.
Okay, sir. Sir, why we're doing all this? From there, if we put x is equal to infinity, 1 over infinity will be equal to 0, and 1 raised to power infinity is equal to 1. And why we're doing
It
all
isn't.
this?
It isn't.
Express.
It isn't.
Why, sir? Why?
The one thing I keep trying to tell you people, do not treat infinity as if it was a real number. It's not an element of the real number system. So I don't know what 1 to the infinity is. One is an element of the set of real numbers. Infinity is this other thing. It doesn't live in the set of real numbers.
Okay.
Yeah.
Isn't that just the formula for compound interest?
Yeah, exponential. Yeah, if your interest was continuous, then yeah.
Yeah, that means that you're just making it infinitesimally smaller now, so it approaches E.
Yeah. Okay. What about this one? Limit as x goes to infinity of 1 plus 2 over x to the x. Okay, how would you do this?
2 times E?
Yeah, well, that's a reasonable
That
guess.
should be e
Okay.
power 2.
How would you do
squared?
this? How would you do this problem?
Take y as like 1, y of x is equal to 1 over 2 over x, and then use the same procedure.
Right.
Either we will end with e square or 2.
Yeah. Okay,
Most
so
probably.
you let y equal 1 plus 2 over x to the x, this thing, this function that you're interested in. Then you can take the logarithm of y as long as you're not dealing with a zero or a negative number. You're not in this case. The x's are positives. Okay, so logarithm of y over x. And the advantage of that is you can pull the x outside of the logarithm symbol. So now you've got a function of x times a function of x, rather than a function of x to the power of a function of x. Okay, so the logarithm of y is x times the logarithm of 1 plus 2 over x. Okay, if I wanted to use L'Hopital's, I have to write that as a quotient of functions. So I'll write that as logarithm of 1 plus 2 over x divided by 1 over x. Okay. All right, so now let's do this again. It's essentially the same thing. Limit is of the logarithm of y is the limit as x goes to infinity of this function. Now this function, once again, the top function would go to 0 as x goes to infinity, and the bottom function would go to 0 as x goes to infinity. So this, I write 0 over 0 in square brackets to say that I recognize this fact, and that I am now going to use L'Hopital's rule. Okay, the derivative of the top function, well, logarithm of something, 1 over the something times the inner derivative is minus 2 over x squared. And on the bottom, the derivative of 1 over x is minus 1 over x squared. Okay, so let's simplify, and minus signs cancel, the x squares cancel. So you get limit as x goes to infinity of twice 1 over 1 plus 2 over x. Okay, 2 over x is going to 0. So this is basically limit as x. This limit is 2. Is that all right so far? Is there a question at this point? Okay, so if the logarithm of y goes to 2, what does y go to?
2x.
Exponent of 2.
Exponential of 2. Okay.
So e squared.
Yeah, e squared, exponential of 2. Is that okay?
Yes.
All right.
Makes sense.
All right. Let me give this to you as a problem, okay? See if you can work out what limit as x goes to infinity of 1 plus 2 over x to the 3x. If you understood the procedure of the previous two problems, hopefully you can do it.
Sir, is it exponential power 6? Exponential 6?
Yes, I think so. I don't remember exactly. Okay. All right. Here, I claim that the limit as x goes to 0 from the right of x logarithm of x is equal to 0, right? Why didn't I write limit as x goes to 0? Why did I write this as a directional limit?
Because it
That
doesn't
probably means that the limit at x approaches 0 doesn't actually exist. So we'll probably have to take directional limits of some sort.
Well, yeah, I mean, I don't want to be taking any negative numbers inside the logarithm, right? So,
Oh yeah, the logarithm isn't actually defined in negative numbers either.
right. So
My bad.
I'm going to take the limit as x goes to 0 from the right of the logarithm of x. And it's not in a form that you can use L'Hopital's right now, right? Because it's a product of functions. It's not a quotient of functions. So what would I do?
Log of
Divided
x
by 1 over x.
Yeah, I rewrite x log of x as logarithm of x divided by reciprocal of x. Okay. All right, so limit as x goes to 0 from the right of x log
Divided
x.
by 1 over x.
Logarithm as x goes to 0 from the right of log of x over 1 over x. Okay, logarithm of x grows without bound, and 1 over x grows without bound. So I say this is of this forms infinity over infinity in square brackets. And I'm going to use L'Hopital's rule. So that's the limit as x goes to 0 from the right. Derivative of log of x is 1 over x divided by the derivative of 1 over x, which is minus 1 over x squared. Okay, let's simplify that. That's the limit as x goes to 0 from the right of minus x. And as x goes to 0, minus x goes to 0. So that's equal to 0.
Sorry,
Okay.
can you go back to the question for a bit?
Yeah.
Can we do it like log x to the power x? And x to the power 0 is 1, and then log of 1 is 0.
Okay. Okay, so if I did it as this is the logarithm of x to the x, then I think you'd have to be able to work out what the limit of x to the x is, right? And you'd have to show that that was equal to 1. I mean, you could probably do it, but
We could do it, right?
yeah, you could do it that way. I think it might it'd just be a few more steps than this approach. Okay, exercise for the student this time. If you understood what happened in this example, then try using the same approach for the limit as x goes to 0 to the right of sine of x times log of x. And that will also be equal to 0. Okay. How about this one? Logarithm of x as x goes to infinity of x to the 1 over x. Well, what's infinity to the 0? I don't know. Okay. So what am I going to do? I'm going to let y equal x to the 1 over x, and I'm going to take the logarithm, right? I've got a function of x to a function to the power of a function of x. Those are awkward to do directly. So I'm going to take a look at the logarithms, because then I can pull the function downstairs, the exponent function downstairs, and then I've got a function of x times a function of x. That'll be easier to do. Okay.
Sir, can you move back to the previous slide?
This one?
The one that had that problem.
Okay, so you have to speak up. I'm not getting you.
Yeah, I need to see. I just wanted to check something.
This one?
No, sir, it's fine. I saw
Okay.
it. You can move ahead.
All right. Okay, so limit as x goes to infinity of x to the 1 over x. Let y of x equal 1 over x. Logarithm of y of x, I can pull the 1 over x downstairs outside of the logarithm. That's 1 over x times the log of x. That's the log of x over x. The limit as x goes to infinity of the logarithm of y is the limit as x goes to infinity of log of x over x. I think we've already done this one, but you know, it has the form infinity over infinity in square brackets for the purposes of using L'Hopital's rule. So derivative of log of x is 1 over x, derivative of x is 1. Limit as x goes to infinity of 1 over x is equal to 0. So if the logarithm of y is going to 0, what is y going to?
1.
Going to 1, yeah. Okay, so the limit as x goes to infinity of y of x is the limit as x goes to infinity of the exponential of the logarithm of y. Exponential is continuous, so pull in the limit sign. And the limit that we just found was 0, so this is exponential of 0, which is equal to 1. Okay. All right. And you might, okay.
So are we done?
Yeah, as an exercise, I would suggest you also try limit as x goes to infinity of x to the x. Okay, so that's it for this session. If you want to stick around for questions. Yeah?
X to the EX?
What's that?
So she's asking about the question, I guess. The one that you said we should try.
Oh yeah, I would suggest try looking at limit as x goes to 0 of x to the x.
And sir, I had a question.
Yes.
Sir, if we put infinity into the exponent x, Would that be illegal? Because that would also yield 1.
Yeah, yeah. The thing is that
It's better to use the L'Hopital's rule.
yeah, you can't just put in infinity into the 1 over x and not put it into the x.
Yeah.
Right? So then you have, yeah. Okay.
Sir,
Any other questions?
Sir, can you go back to the place where you had that exercise for us? I didn't note that down.
Okay. This one?
Yes, sir. Enter a previous one. I guess 1 plus 2 over x raised to power x.
It was this one.
All right, sir.
Okay.
Sir, can I have its answer as well? I just want to match my working with that.
Okay, wait. Do you want to go to another page?
So I just want to know its answer so that I can match my
Oh,
answer with that.
I don't remember, but I think it's like e to the 6th
Exponent.
power.
Yes, sir. I got the same answer. E to the 6.
Yeah. Okay.
Sir,
Yeah.
then the last class you told us that you had checked our papers midterms. So
Yeah.
you have any idea when will we be getting them back?
Yeah, no, I don't know. I think it's with the TAs now.
Okay.
All right. If there are no more questions, then I will see you next week.
Sir,
Yes?
sir, I'm sorry to say this disconnected. Midterm के marks हमें कब पता लगेंगे?
Yeah, I'm not sure. I think it's with the TAs.
Okay, that's all right. Thank you so much.
All right. Okay. I'll see you all next week.